All right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Pretty good.
This is good to hear. All right, so today is just a pure lecture day. So yesterday we had our first activity in ANSYS. So remember that is due this Sunday. So make sure you guys are working on it. Our next ANSYS activity will be on Tuesday. So we're gonna do 2 activities next week. So one on Tuesday, one on Thursday, just to kind of catch up a little bit. But today we're just going to do a pure lecture. Okay, so for the first half, we'll be talking about boundary conditions. So that's another kind of essential ingredient to a finite element simulation. Yesterday we went over meshing, which is the first part. Today we're going to do boundary conditions in the first half and then material properties in the second half. Okay. So a little bit of what we covered today is going to be a bit review of what we went over on Tuesday. Just because remember on Tuesday we kind of introduced these ideas, mostly just so that we can get that prerequisite knowledge to do the first ANSYS activity. But we are going to go a bit more in detail in terms of what these actually represent and all the different options that you have for these settings in ANSYS and just finite element simulations in general. All right, any questions I can answer before we get started for today? Okay, all right, so let's talk about boundary conditions. Okay. So if you recall from the activity yesterday, there was a certain point in the activity where we had to apply boundary conditions, right? Let me just kind of refresh your memory. So yesterday we had our plate with a hole. Okay. And we had to apply boundary conditions on the left side of the plate and the right side, right? So on the left side, we applied what's called a fixed support. Right? Basically, what we did was we assumed that that side of the plate was fixed, and so it would not move, and so there was no deformation involved on that left-hand side. Whereas on the right-hand side, we applied a tensile pressure. Okay. Then right after that, we ran the simulation and we were able to view the results. Okay. Now, both of these, even though obviously their effect on our geometry is different, they both have the same thing in common, that they're both boundary conditions. And so just to kind of jog your memory from a couple days ago, boundary conditions are the way that we're going to model or encapsulate any kind of external effect on our geometry. So basically, if there's any kind of external force or external constraint that's going to be affecting the behavior of our finite element geometry, which for a structural simulation means that anything that's going to affect the deformation or induce stress within our geometry, we are going to encapsulate that as a boundary condition. Okay. Okay. So I think physically, the intuition for a boundary condition is kind of more or less straightforward. The fact that, whatever geometry or whatever system that we're looking at, it's going to be subjected to external effects, right? But boundary conditions actually have a mathematical reason as well. Okay? So the concept of a boundary condition is not unique to a finite element simulation. In fact, hopefully you've heard the term in some of your previous classes before. Maybe your solid mechanics class and your fluid mechanics class. If you've taken heat transfer, you've probably heard of that term there as well. Okay. Because remember, at the end of the day, finite element analysis is just a way for us to solve the governing differential equations, right? Anytime that you have a differential equations, you need to have a boundary condition, or a lot of times several boundary conditions, in order to form a full solution. Okay, so let me do an example just to kind of show you. So you've definitely done problems like this before in your previous classes. So either be Math 250B, or maybe you've taken 308 as well. Okay, so let's look at a very simple differential equation, one that we can actually solve by hand. Right, so we have d squared u dx squared is equal to 3x squared. Okay. And so our objective in this problem here, mathematically, is to solve for the solution u of x. Right, so very, very typical differential equation problem. And the nice thing about this problem here is that, we don't need to use any special tricks, like we don't need the characteristic equation, we don't need an integrating factor. We can just straight up integrate this just because it's an explicit expression for the derivative. Okay. All right, so let's go ahead and just do that. So let's go ahead and integrate this once. Okay. We're going to integrate it. We're going to integrate both sides of this equation with respect to x. Okay, so on the left-hand side of the equation, that integral is going to cancel out with one of the derivative orders. And so on the left-hand side, we just end up with a first-order derivative with respect to x of the function u. And then on the right-hand side, we're going to take the integral of 3x squared, which is a function of x, and so we can integrate that. Okay, so we do just our basic antiderivative. We increase the exponent of the x by 1. We divide by it. We end up with x cubed. Okay. But, since we are doing indefinite integrals here, and indefinite meaning that we don't apply any integration bounds, right? We're just doing just a generic integral. We have to also add a generic constant as well. Right? Or I think usually I call this the arbitrary constant. Right? So anytime you perform an indefinite integral, right, it's not complete until you add that arbitrary constant, right? And it's there because, when you take the derivative, remember the derivative of a constant is just 0, right? And so if we were to try to return this to the original equation, if we were to take the derivative of both sides with respect to x, then that C1 term would go away because we're taking the derivative of a constant, okay? All right, so let's integrate this one more time. Remember, our objective is to solve for u of x, not du dx. Okay. So once again, on the left-hand side, our integral is going to cancel out with one of the derivative orders there. So we end up finding with u of x. Okay. Right-hand side, we're going to integrate each of the terms individually. So integral of x cubed with respect to x is 1/4 x to the 4th. Okay. We take the integral of our constant c1, we get c1 times x. Right? And then once again, since we're doing an indefinite integral on that side, we need to add a second arbitrary constant. So we have another c2. All right, and so by doing so, we obtain this expression here, remember, which we usually call the general solution. We call it the general solution because, it's only specific up to the values of these arbitrary constants, C1 and C2, which at this point could be anything, right? So C1 could have the value of 7. It could also have the value of, 11 million. And our expression would still satisfy the original differential equation, okay? Okay. But most of the time, we don't leave it like this. And so when we want to solve for a differential equation, we want a very specific we want a very specific expression, and that involves, of course, computing the values of C1 and C2. Okay. And the way we did that was we applied our boundary conditions. Now, you may not have called this when you took your math class or your 308 class, but essentially they form the same purpose here. Okay. And the boundary conditions, if you think about the role that boundary conditions play in our finite element simulation, right? Boundary conditions specify the condition of the solution at specific locations. Okay. And so mathematically, they're going to play the same role here, right? So mathematically, we can think of boundary conditions as basically specifying the condition of the solution at specific locations, which in this case is going to be for specific values x. Okay. And so by doing so, we can solve for the values of our arbitrary constants C1 and C2. Okay. So for example, let's try this boundary condition here. Okay. So let's say our first boundary condition is u of x is equal to 0 is equal to 18. Okay. Right. So in other words, the way that we can interpret this is that when our x is equal to 0, then our solution must take the value of 18. Right. So that's kind of what that statement there says. Okay. Okay. So let's just go ahead and plug in for that, and then we'll be able to solve one of the constants there. So let's take our general solution and then plug in x is equal to 0. Okay. Right. So we apply x is equal to 0, we get 1/4 0 raised to the 4th power plus C1 times 0 plus C2. Right. And so by our boundary condition, this expression here has to equal 18. Okay. And so very easily we can see everything that's multiplied by 0 is just going to cancel out. Right. And so we're left with the expression that C2 must equal 18. And so by applying this boundary condition, we can then specify the value of one of our arbitrary constants. Okay. Okay. Good. So now that we know C2, we just need another condition here to specify the value of C1. So let's apply another boundary condition. Okay, so for our other boundary condition, let's say that the derivative of our solution, so let's say du dx, evaluated at x is equal to 10, is equal to minus 5. And so in words, the way we can describe this is that when we're at the location x is equal to 10, the derivative of the solution must equal to minus 5. Okay, so let's go ahead and do just that. And so we do need to take the derivative of our general solution here, right? So we take du dx of our general solution. right? So our general solution being this expression up here, the 1/4 x to the fourth plus c1x plus c2, okay? So taking the derivative of this, of course, is going to cancel out the c2, and then everything else we have x cubed plus c1, okay? Let's evaluate this expression, x is equal to 10. So du dx at x is equal to 10 is equal to 10 cubed plus c1. Okay. And then according to our boundary condition, this must equal to -5. Okay. All right. And so we just do a little bit of arithmetic. We see that 10 cubed is equal to 1,000, right? So 1,000 plus c1 is equal to -5. We can then solve this expression very easily for c1. C1 is equal to -1,005. Okay. Okay, so we plug both those in and then we get our complete solution, right? So we plug in for C1. So our U of X is equal to 1/4 X to the fourth minus 1,005 times X plus 18. So this right here is our complete solution. All right, so I know you probably didn't expect to get a refresher on differential equations today, but I wanted to do this kind of very simple example to kind of illustrate to you why boundary conditions are necessary from a mathematical perspective. Okay. All right, any questions on this example here? By the way, I noticed a lot of people are on Zoom. I don't have speakers here, so if you do have a question, just drop something in the chat. If you do need time to kind of type your question, just I know it takes a while. Just type something very quickly in the chat. Just say wait, and then I'll wait a second for you to type that. Okay. All right. So let's go ahead and continue. So remember, finite elements. Finite elements essentially is just a method for solving differential equations. It's just we're solving much more complicated equations on much more complicated geometries, but the mathematical requirements are the same. Okay. And so because in FEA we are solving these governing equations, boundary conditions are needed in order to form our complete full solution. Okay. And so in fact, some of you may have picked up on this yesterday during ANSYS activity 1, right? ANSYS won't even let you run a simulation unless you apply some boundary conditions, okay? And so, you always, a boundary condition, you always need at least one boundary condition. Oftentimes you need multiple in order to run an FEA simulation, okay? And in fact, I like to kind of think of it like this, and I think this kind of framework is very useful for thinking about boundary conditions, both from a mathematical perspective and a physical kind of intuitive perspective. Okay. Okay. Remember, boundary conditions, at least physically, the way that we're interpreting them, they are any external effects that are going to be affecting our system. Okay. And so one way that you can think of it is that boundary conditions provide the impetus, so they provide the input in order to cause our system to react. So in some ways, you can think of the boundary conditions as being the cause of any kind of interesting deformation or stress behavior that you're seeing in your system. Okay. And if you think about it from this perspective, where, for the most part, most structures are just kind of chilling, right? And so, if you don't provide any kind of force or any kind of external effects, a structure isn't really doing much, right? So if you're at home right now, you see just an object on your desk, right? That object isn't really doing anything because we're not providing any kind of external effect. We're not providing any impetus, okay? So the boundary conditions are what provide that kind of, input to cause our system to either deform or have stress the way that it does, okay? Our governing equations, right? The governing equation that we're assuming will describe how our system is going to react to the boundary conditions. And actually, I'll go ahead and throw in the material properties as well, just because we'll be talking about that later today. Okay. So whether you have an aluminum rod or a rubber rod, right, those are going to respond differently to an applied force. Whether you're considering a linear elastic situation or thermal situation, that's going to describe how your system's going to respond to it as well. Okay. Okay, so before we kind of get into more of the details in terms of the types of boundary conditions, I at least wanted to kind of introduce boundary conditions and explain why they're needed and kind of just the framework of the way that I typically think about them intuitively. Okay. So this first whole section here was just kind of introducing what boundary conditions are and why we need them for FEA. Okay. All right. Any questions before we move on to the next points? Okay. All right. So let's go ahead and get into the types of boundary conditions. And so, if you recall from yesterday's activity, there are a lot of different types of boundary conditions that you can apply within ANSYS. And we're not going to go through every single one of them just because, for the most part, you're not really going to use most of those. A lot of those specific boundary conditions in ANSYS are for very niche situations. But I do think it's useful to think about the categories of boundary conditions and the effect that they have on the solution. Okay. So there are two types of boundary conditions that I like to think about. So the first type of boundary condition that I think about are what I call constraint type boundary conditions. Okay. The other type of boundary condition that you are most likely to see are load type boundary conditions. And of course, so this naming convention here takes, kind of assumes that you're running a structural simulation. And so I will say that this naming convention, I wouldn't say is standard. But I think that this is the way that I kind of think about it, at least within the context of this class, within the context of, structural simulations. Okay. Now, these types of boundary conditions do have kind of official mathematical names. I won't use them for the most part, just because I think they're not very descriptive, but in case you were curious, constraint type boundary conditions are often called Dirichlet boundary conditions. Okay, so you spell it just like that. So it looks like Dirichlet boundary condition, but it's pronounced Dirichlet. And then load type boundary conditions are often called Neumann conditions. So they're named after the mathematicians that I guess formalize the theory for these boundary conditions. So, sometimes if you read finite element academic papers, they'll refer to it using this convention here. But I think within the context of this class, it's not very that useful. So I refer to them as constraint type and load type. Okay, so we're going to go through each of the types, and then first of all we'll talk about what type how those types of boundary conditions manifest themselves in ANSYS. And then we'll also talk about mathematically how they affect our solution. Okay, so let's start with constraint type boundary conditions. Okay. All right, so constraint type boundary conditions are basically conditions that directly specify our primary solution variable. So any type of boundary condition where we're directly specifying, we're saying that the solution has to be this at this location, I consider that a constraint type boundary condition. Okay. Okay. So there's a few kind of layers to this statement here that I want to kind of expound upon. So first being directly, okay? So a direct specification basically means that your solution has to be this, okay? So if we think back to our previous mathematical example, we did actually have a constraint type boundary condition there, okay? Right? And so if we look back at our example, we had one boundary condition which stated that u at x is equal to 0 has to equal to 18. Right? So this is very obviously a constraint type boundary condition because our solution value, which is u, right? So u is the, what we're solving for in the differential equation. What we're saying is that at the location x is equal to 0, u has to be 18. There's no room for ambiguity at all. Right? So that's what it means to directly specify the value of our solution. Okay. Now, the other kind of layer to this statement here is actually this term right here, solution. Okay. So when you look at a very simple mathematical example that we did there, it's very clear that u is our solution. Okay. But if you're running an ANSYS simulation, what do we consider our solution, right? So if you think about kind of what we did yesterday, right, we looked at actually quite a few solution variables. And so we looked at the deformation, we looked at the stress, we looked at the strain, right? So what does it mean to have, to specify value of the solution? So if we set the stress or we set the strain to be equal to something, is that a constraint type? Well, it turns out in every finite element situation, and I guess technically for every every boundary value problem, there is what's called a primary solution variable. And it's not necessarily something that the software will tell you, at least not directly. It's kind of something that you kind of have to just know from the theory. Okay. And so primary solution variable is the variable or the unknown that is solved for first in the finite element simulation. Okay. So again, it may not be obvious because when you're kind of just clicking buttons within ANSYS, it kind of feels like just everything just kind of happens at once. So you obtain the deformation field, the stress field, the strain field, you obtain all those at once. But actually, underneath the hood, there is one solution variable that's actually solved for first before everything else. And technically speaking, all the other solution variables are derived from that primary solution. Okay. So for structures, which again is the primary equation that we're going to be solving in this class, the primary solution variable is the deformation. Okay. All right. So when we're talking about constraint type boundary conditions and just knowing the fact that our primary solution variable in structures is the deformation, any boundary condition that directly specifies the deformation value is what I would consider a constraint type boundary condition. Okay. Okay. So in our first ANSYS activity, we had one constraint type boundary condition. And hopefully after this description, it's pretty clear which one it is, right? So let me just kind of scroll back up here, right? So the two boundary conditions that we applied in our first activity was we applied a fixed support on the left-hand side and a tensile pressure on the right. Okay. So between these two, the one boundary condition that I would consider a constraint type is the one on the left, which is the fixed support. Okay. So fixed support boundary conditions are actually going to be the most common constraint type boundary condition that you're going to specify. I think almost every ANSYS activity that we're going to do is going to have a fixed support boundary condition. Okay. So fixed support is a constraint type because it sets the deformation values to be 0 at whatever location we're applying the fixed support. Okay. And if you look back on your results from our ANSYS activity 1, right, you'll see that that's consistent, right? So if you look at the deformation field for all parts of the activity, right, you'll see that along that left edge, the deformation is 0 because we're applying that fixed support, that fixed constraint boundary condition at that location. Okay. All right. Any questions on this so far? Okay. Okay. Good. All right. So constraint types, very important for these FEA simulations. In fact, every finite element simulation has to have at least one constraint type in order for it to be valid. There are niche situations where you can get away without applying a constraint type boundary condition. Most notably, if you're able to apply forces in such a way that all the forces cancel out, you can get away without a constraint type. But I always give this statement here because otherwise it just becomes very tricky. So for every simulation that you run, you should expect there to be at least one constraint type. 99% of the time, it's going to be a fixed support. But you can actually directly specify a non-zero deformation as well. It's just that those get a bit more complicated as well. Okay. And this makes sense physically too, because without a fixed support or without a constraint, you're going to get rigid body motion. Okay. So to give an example, let's look at a typical beam. Right. So if we look at a simply supported beam right here, we have maybe a pin support on the left-hand side, and then let's put a roller support on the right. Okay. Okay, if we were to apply a tensile force, so let's say that we apply a force going to the right here, okay? We expect this beam is going to elongate, right? So, kind of similar to our plate with the hole, applying a tensile force is going to force the entire structure to elongate, okay? Now, the reason this works is because, we have our constraint here, okay? So here, this pin support is preventing any kind of horizontal motion for the entire beam. So after we apply that tensile stress, right, the beam is going to elongate, but it's not going to go anywhere, right? There's going to be no rigid body motion. If we didn't have that pin support there, right? So let's say that we change that to a roller as well, right? And so we change this support to a roller instead of a pin, right? That roller is not going to provide any resistance or any constraint in that horizontal direction, right? So if we have two roller constraints and we apply a tensile force, right, this whole beam is going to be, it's not going to stay still. It's going to be making its way downtown, and that's typically what we don't want. We typically want our structures to stay still. Okay. Okay. So if you try to run a simulation like this with an ANSYS with two roller supports, ANSYS is going to give you an error because it's going to say that it's literally going to say that rigid body motion is not prevented in this case. Okay. Okay. Good. And we can see this mathematically as well, right? And so if we took a look at our previous mathematical example and we replaced the constraint type boundary condition with something else, you're going to see that it would be impossible for us to actually solve for the full solution. Okay? If we look back again, right? So I'm not going to do this fully just because I think we've done enough math for today, right? So if we look at our general solution that we found from above, right? So we solved our differential equation. We ended up with this general solution here, right? So 1/4 x to the fourth plus c1x plus c2. Okay. Remember, we had two boundary conditions for this. So we had one, u of 0 is equal to 18, 2, du dx at x is equal to 10 is equal to -5. Okay. So we've already established here that our constraint type boundary condition is the first one, right? U of 0 is equal to 18. But if we were to change this boundary condition, so instead of being a constraint type, what if we change it to a derivative boundary condition instead? Okay. What if instead we had du dx at x is equal to 0 is equal to, I don't know, we can say 10. Doesn't really matter what the value is. Right? If you go through the problem, right, so you kind of go through the exercise of applying these boundary conditions, what you're going to see is that both of these boundary conditions, the du dx is equal to 0 at x equal to 0 is equal to 10, and the other condition on the derivative at x is equal to 10, right? These conditions are going to be incompatible. Not only that, it's actually impossible for us to solve for the value of C2. Okay? right? So mathematically, the constraint type boundary condition is required as well, okay? Because when you solve a differential equation, there's inevitably going to be a constant, I call kind of a bias term or a reference term, okay? And without a constraint type boundary condition, it's actually impossible to solve for that value, okay? So a constraint type always is going to be required. There's no getting around that at all. So, you can't run an FEA simulation, you can't solve a differential equation without at least one constraint type boundary. All right, so before we move on to load type boundary conditions, just a few more pieces of information here. So like I mentioned, the fixed support is going to be the most common constraint that you're going to be applying in your ANSYS simulations. Another type of constraint type boundary condition is what's called a displacement. Okay? Right. So it's not used much. Honestly, for anything that I've done, I've never used a displacement boundary condition, but it is possible. So maybe you're in a situation where you know what the displacement is going to be at a particular location. So it's going to be a non-zero displacement. So you can apply that, and that counts as a constraint type because we're directly specifying the deformation by directly specifying the displacement. Okay. And then if you're going to run a heat transfer simulation, a thermal simulation, for a thermal simulation, the primary solution variable is temperature. Okay. So any boundary condition that specifies the temperature, there's literally a temperature boundary condition that you can apply for a thermal simulation. I would consider that to be constraint type. Okay. All right. And then, I mentioned that just because I know some people like to do thermal simulations for their final project. If you wanted to do a fluid simulation, I get maybe a one or two of those, every 2 years or so. The primary solution variable for a fluid simulation is the velocity and pressure. And so any condition that applies, a condition on the velocity, sorry, it's just velocity, not pressure. Any condition that applies a condition on the velocity counts as a constraint. Okay, but fluids is quite rare. So if you did want to run a fluid simulation for your final project, maybe we'll talk offline and we'll set it. All right, any questions on this before we move on to load type boundary conditions? Okay. All right, so let's go on. Let's move on to the other type of boundary condition that we see, which is the load type. Okay. So the definition of a constraint type boundary condition is pretty clear. It's pretty straightforward. It's just anything that's directly specified the solution value. A load type boundary condition is not as clearly defined, and so a load type you can kind of consider as kind of everything else, anything else that can affect your solution. So basically, any other external effect that can influence your solution variable, I count that as a load type. So any external effect that can affect the solution variable without directly specifying it. So a load type boundary condition can take many, many different forms, and they all kind of affect the solution differently. I used to, I used to use the definition in the past to say that load type boundary conditions take the form of a derivative mathematically, but that's not necessarily true all the time. It is true, often. So, like a force type boundary condition or a pressure type boundary condition, essentially we're specifying a condition on the derivative. But there are other types of boundary conditions that, without directly specifying the solution variable, still influence the solution. And so I would categorize those as load type. So any external effect that affects your solution, without directly saying that the solution has to be this at this location, I would consider that as a load type. Okay. All right. So some common examples that we will see in ANSYS. And so, we've already used one in our previous activity, like a pressure. Pressure is essentially just a distributed force, right? So we know that when we apply a force to a structure, it's going to cause it to deform, but it's not causing it to deform directly, right? So we're not saying that the pressure is going to force a deformation to be X, right? We're just applying the pressure, and we're going to see how the structure deforms as a result. Okay. All right. Another very common type is a force. Okay. So we will see that in our ANSYS activity 2 on Tuesday. Okay. So the way pressure and force are applied are very similar. The only thing that's really different between them is just the unit. So pressure is a force per area, whereas a force is just a force. Okay. Often having units of newtons or pounds, whereas pressure is expressed as Newton per meter squared, which is a Pascal, or oftentimes in English units as pounds per square inch or PSI. Okay. Sometimes also pounds per square foot as well. It depends on the image. Okay. All right. And so I would say the majority of boundary conditions that you see within ANSYS kind of fall into this load type because they're not directly specifying it. And they are important, but technically speaking, they're not required. So you can technically run a finite element simulation without a load type, but very commonly you're going to have a load type boundary condition because that kind of is most intuitive in most situations. Okay. All right, so a way that you can get a simulation to run without a load type. So let's say that you can run basically two constraints, right? So you can say that there is a constraint on one side, a fixed support, and then a non-zero deformation on another part, right? So that's a valid simulation configuration. But most commonly, you're going to have a fixed support as a constraint and some kind of force or pressure that's going to cause your system to deform. Okay. Okay. Let's see. All right, so with load type boundary conditions, the most important thing to consider with the load type is to make sure that the condition that you're applying, that means the units, the direction, and the type of load type boundary condition is most consistent with the physical situation that you can be. Because ultimately, ultimately your finite element simulation is a prediction or it's a simulation of a physical phenomenon, right? And so you want to make sure that the boundary condition or the load that you're applying is consistent with your the physical situation that you want to predict, okay? Because if it's not, right? So let's say that you don't input the force correctly, right? You're not going to get a result that's going to be useful to you because it doesn't accurately portray, the situation that you're trying to simulate, okay? Which may seem obvious, right? So that's a very kind of a very long-winded way to say, don't make the force incorrect, right? But there's a lot of nuance here. There's a lot of things that you can kind of get incorrect. So just a few considerations off the top of my head that I kind of see most common, right? So, whether you want to apply a force boundary condition or a pressure. You can technically get the same result with both, right? But the units are going to be different and the values are going to be different depending on whether you apply a force or a pressure, okay? Sometimes a force makes more sense depending on what you know about your physical situation. Sometimes a pressure makes more sense, okay? I will say, one thing that, someone always points out, usually later in the semester during activity one, that the way that we apply the load in activity one actually is a little bit awkward if you think about it, right? So we have this, essentially two-dimensional situation so our thickness of the plate is very small. And so to apply a pressure in that situation when you don't have a very large application surface, technically we only have just an application line. Physically that's a little bit awkward, right? Probably in that situation, a force probably makes a bit more sense, just because it's a little bit easier to quantify for a small thin surface like that. Okay. So whether you use a force or a pressure, that's not true. So make sure that you pick the right one and make sure that it makes the most sense for your physical situation. Okay. Next thing to consider, obviously, is the value of the load. Okay. So you want to make sure that you get the value correct or the magnitude of the loading correct, right? And that includes the units. So don't just blindly put in, 1,000 into the ANSYS software. Make sure you're putting 1,000 pounds or 1,000 newtons because that does make a difference. Okay. So make sure you're paying attention to the units when you're plugging that in. Okay. And that goes for the material properties as well. And I always say this every year, but so there's always at least one person in activity two that puts in the wrong value for the material properties because they have the wrong units. Okay. And that goes for the force as well. Next is the direction. You want to make sure that your direction is correct. And it's not just as simple as applying a tensile force or compressive force. A lot of times you're going to have forces that go in somewhat of an oblique direction based on your physical situation. So you want to make sure that you check the direction to make it correct. Okay. And so if you remember from yesterday, right, the way that we applied the force yesterday was we changed the force application to component. So in my opinion, I think that's the most fail-safe way to apply your force boundary conditions because it forces you to think about, what's the X component, what's the Y component, what's the Z component. Because if you don't do that, right, ANSYS kind of just lets you put in a number, then you essentially let ANSYS pick the direction for you. And you don't want to do that. You want to make sure you're very explicit in terms of which direction you. And so I'm going to put this in red because I think it's the most fail-safe way to apply the forces to use that component. Okay. Okay, so those are just a few a few of the considerations that you need to apply or think about when you're applying your load type boundary conditions. Applying the load type boundary conditions is straightforward, but getting it wrong is just as easy as getting it right. So you want to make sure that you get this correct. Otherwise your solution is going to be worthless. Okay. Okay. All right. Any questions on this? Okay. And so this is also one thing that, as you kind of do more and more finite element simulations, this is something you'll get practice in. Like I mentioned, the last couple of days, that with finite elements, you're no longer in the driver's seat, I guess you can say. You're no longer the ones solving the problem. Instead, you're setting it up, right? And so you want to make sure that the setup is correct before you actually run the simulation. And I think, sometimes it takes a little bit of time to kind of get used to that mindset. Okay. All right. So I just have a few more points to make before we go to break. One thing I do want to make note of is that, you don't need to apply a boundary condition on every single exterior surface of your mold. Right? As our geometries get more and more complicated, you're going to see that there's going to be more and more surfaces for us to potentially apply boundary conditions, but you don't need to apply one on every single surface. You only need to apply boundary conditions on surfaces that are going to be experiencing that's going to experience some kind of external effect. Okay? So I bring this up just because, technically, mathematically, you do need a boundary condition on every single surface in order to get a solution, right? And so if we were to solve the full partial differential equations, we need to have a boundary condition on any surface that's facing exterior, okay? Any kind of boundary in our system. But one thing that ANSYS does, and actually most finite element software will do this, for any surface or any kind of external part of or any boundary in our system that we don't apply boundary condition to explicitly, there is a default boundary condition that it applies. It's not something that we think about, and once I kind of reveal what it is, it's very intuitive. It's like, oh, of course it does that. Okay, but I do want to let you know that it does do that. You don't have to do this manually. I had a couple people throughout the years do this, and it kind of ends up just being a lot of work for nothing. Okay, so the default boundary condition that ANSYS applies to any surface that we don't specify is what's called a stress-free boundary condition. Which essentially means that there's no force being applied there. Okay, so technically it's a load type boundary condition, but it has just a load of 0. Okay, so it can't be a constraint type because we can't, without any information, we can't specify what the value of the solution would be. But we can at least apply a stress-free boundary condition. But that's applied by default. So you don't have to do that. All that really means is that there's no external effect or there's no external, something that's affecting our solution at those locations. Okay, but I did want to make note of that just because sometimes I have someone that applies boundary conditions everywhere, but that's not strictly necessary. Okay, good. All right, so before we go to the break, I do want to mention a couple more, I would say, kind of practical considerations when applying boundary conditions. So, what we've covered just now is just kind of more of a background, kind of more background information about what the boundary conditions are and why they're necessary and what they actually do. But, again, as a user of finite elements, you're kind of more interested in kind of more just the practical application. Okay. So let's talk about a couple of those before we head to break. Okay. So the first practical consideration actually just kind of goes back to the point I just made about loads, right? The boundary conditions that you specified, and this goes for the constraint type and load types, have to be as physically consistent with your underlying physical situation as much as possible. Which again is going to seem obvious, but and honestly, probably this is probably not something you're going to think about until you guys work on the projects. Just because at least for the activities, for the most part, for the activities, I'm going to be providing you with the boundary conditions, and so it's not something you're really going to think about. But when you're applying ANSYS, when you're applying finite elements on your own, you may run into some actual difficulties because you may run into situations where maybe your physical situation is either complex or maybe if not all the information is known, where maybe there's not a boundary condition that perfectly encapsulates what you want to do or perfectly kind of models your physical situation. Right, so just a very simple example, right? So let's say you have a situation where there's going to be an applied force and it's distributed over an area, but it's not going to be a constant force. It's going to be a force that kind of varies kind of location to location. Maybe that there's going to be more pressure at, maybe down the shaft more than this place, right? So how do you apply the pressure type boundary condition in that case? Um, so in those situations, there are kind of more advanced features within ANSYS where, maybe there's an advanced boundary condition that you can apply that kind of applies more niche to your situation. We'll see one of those in activity 6, the very last activity. We'll use what's called a bearing load. And so that is different than a typical force. Okay. But you may run into a situation where you may have to make an assumption, right? You may have to simplify your real life situation just so that you can apply it in FEA. Okay, so don't be afraid to do that. Okay? Maybe you simplify. So maybe maybe you have kind of a complex constraint on your system, right? But it's just a lot simpler to apply that as a fixed support over a wide area. Okay. So you may have to do that in those situations. And, I can't tell you right now how valid that's going to be just because, it changes based on the situation. Some assumptions are more valid than others. The only advice I would give is that, go ahead and try it and then, look at your results and think about whether the results that you get are reasonable or not. We'll discuss this later on in the session when we talk about verification and validation. You always want to check your simulation results to see if they're reasonable. And there are ways that you can do that, but don't be afraid to to make those kinds of assumptions. Right? Okay. Number two. All right. So when you're given a choice about where or how you want to apply the boundary conditions, you want to apply them usually in as wide an area as possible while still following number one. Okay. So for example, if you're given the option to apply a force, and you can either apply it at a single point, you can apply it along an edge or across the surface, you always want to choose the surface. You want to try to distribute the force or load as much as you can. Right? And so if you have, the option, so let's say that you have a surface here, where you have the option of either applying that single force on a single point, or apply it on an edge, okay? Or you have the option to apply it across the entire surface, right? Granted that it's correct, that it's consistent, right? It makes sense to apply it on this entire surface here. You always want to apply it on the surface, right? And if that's not possible, apply it on an edge, right? And if that's not possible, the last resort is to do a point force, okay? Right? So the preference is something like that, okay? Sometimes it's unavoidable. Sometimes you have to apply a force at a point, but you want to avoid those situations, okay? Now I mentioned this just because, I would say, in probably in your solid mechanics class and your statics class, you're probably used to the kind of the practice of computing what's called an equivalent force, and you apply that equivalent force at a point. And so that analytically is beneficial to do just because it makes things simpler to compute. But for FEA, you actually want to distribute that force on as wide an area as possible. Okay. And this has nothing to do with physical consistency and physical accuracy. This actually has more to do with the stability of the simulation. Okay. Generally speaking, if you concentrate a very large amount of force at a single point and there's no force applied at any place around it, that can lead to some more numerical, I guess to kind of put it lightly, just to numerical difficulties. Okay. So ANSYS does have some safeguards against this, and so we'll actually see this in activity 3. We actually are going to apply a point force on activity 3, although it's not the best way to do it. And so you're going to see that the simulation will still be fine, but you actually run the risk of your simulation kind of failing if you apply too many of these point forces. Okay, so try to avoid it. Try to apply your forces on a surface if you can. But sometimes it's unavoidable. So where you see this the most is that oftentimes, people will want to apply a force directly onto like a corner of your geometry just because a corner is very easy to pick out. But try not to do that. Try to see if you can apply that on a surface or an edge instead. And you'll see that your simulation will be more stable and less and more likely to converge in situations. Okay. Okay. All right. And then one last point before we head to break. Okay. Okay. So the last point here is for kind of a very niche situation, but it does come up sometimes. So when you apply a constraint type boundary condition and a load type boundary condition at the same location, the constraint type boundary condition will always win. That's the one that takes precedence. So generally, you want to avoid situation like this. Sometimes you may want to apply multiple loads at the same location because they represent different external effects. That's okay, but you don't want to apply a constraint and a load at the same place. Okay. Okay, so just to kind of illustrate this to you very simply, right? So let's look at our simply supported beam one more time. Right, so we have a fixed support here on the left-hand side and a roller support here on the right. Okay. If we were to apply, okay, if we were to apply a force directly onto the location of that fixed support there, okay, we know already, based on the fixed support, that at this location, deformation is going to be 0. And so even if you apply a force there, it's not going to cause any deformation because we're directly saying the deformation has to be 0 there. Okay. So in a competition between the constraint and a load, the constraint is always going to win. Okay. Okay. So this last point here, not going to come up in any of the activities just because, again, I'm kind of giving you the boundary conditions for the most part for the activities, but it may come up in your project. Okay. So just be careful if you're going to be doing that. Right. And so in those situations, you might want to think about, does this location for the force make the most sense? Or does it make more sense for me to apply the force at a different location so that I can actually see its effects? Okay. All right, any questions on this? Okay, all right, so let's take a break. So we'll come back at 4:30 and then we will continue on with material properties. Right, it's 4:30. Let's get back to it. All right, so we just finished talking about boundary conditions, and so the last, I would say, ingredient in a finite element simulation, at least on a basic level, are the material properties. Okay, so it's actually kind of nice. We're kind of ending this first week. I would say, after this week, we're done with kind of the basics, and then next week we can kind of get to more, a little bit more detail on some stuff. Okay, so let's talk material properties. Slide which we turn on. Okay. All right. So when we say material properties in FEA, what we're referring to are the physical parameters of the material that affects how it responds to external effects. Okay. All right, so every material that's out there has its own set of properties, and those properties are going to, affect its response, right? And so intuitively, we kind of understand this. So different materials just respond. They have different strengths. They have different flexibilities. They have different ways to conduct heat, right? And so, of course, if we're going to be running a finite element simulation that is supposed to be an accurate prediction of how a system is going to perform, we have to specify its material properties correctly as well, because those material properties are going to have a strong impact on the solution. Okay. Okay. So mathematically, so everything kind of comes back to the governing equations. Mathematically, the material properties end up just being constants and parameters that affect different components of our governing equation. All right, and so our governing equation, if you looked at their mathematical form, there's going to be certain terms or certain expressions within the governing equation that are scaled by things like the Poisson's ratio or like the Young's modulus. Okay, and so depending on how those terms are scaled, that's going to affect our solution. Okay. Okay, so when most people think of material property, they think of the values of certain constants or certain properties, right? And so if you think back to our activity one yesterday, right, the two material properties that we were looking at were primarily the Young's modulus and the Poisson's ratio. Okay, so those are the only properties you need for a given material model. Okay. But I think what most people don't really think about is that, when we say material properties, we also are referring to the type of model that we're using for the material as well. Okay. And there are lots of different types of models that are out there. Most are going to be way beyond the scope of this class. And so for this class, for the most part, we're going to stick to linear elasticity. But I am going to kind of mention a lot of other ones here that are certainly viable and certainly more appropriate for other common materials. Okay.
Hey, Professor. When we get further into it,
Oh, go ahead, Chris. Looks like my speakers do work.
okay, excellent. I was just wondering, can we actually like specify all the way down to like the square-bodied aluminum that we use for structures? Is that like a selection within the program?
Oh yeah, yeah. So certain materials are kind of loaded by default, and so we'll actually see that in our activity too. And so if your material, I would say, is a fairly common one, you can select it from the list within the within ANSYS itself. But there also are different ways to apply different material models and different material constants, depending on the material that you're working with as well.
Okay, excellent. Thank you.
Okay. Also, I don't know if they've installed the speakers recently, but in the past the speakers have never worked. So, but that's good to know that it works and I can hear you guys. So, okay. So a model today, so you would think that electron material properties would be fairly short, just because there were only two properties that we looked at last time, which is Young's modulus and Poisson's ratio, which we are going to talk about today. But a model today is actually also going to be mentioning the different types of material models that are out there. So isotropic elasticity, orthotropic elasticity, and isotropic elasticity. We'll talk a little bit about plastic deformation as well. And then at the end, we'll probably mention a bit about hyperelasticity, depending on how much time that we have left this one. Okay. Okay. But to start, let's start with the most common material model that you'll be using in ANSYS, which is linear elasticity. And I would say, for the most part, most solid mechanics classes are focused a lot on linear elasticity. Okay. Okay. So linear elasticity, these refer to certain materials where the relationship between stress and strain is purely linear. So we went over this a couple days ago, right? So these are situations where if you look at the stress strain plot, we have just a straight line that shows their relationship, where the slope of this line is the Young's modulus E. Okay. So for a linearly elastic material, there are two properties that you need to specify in order to fully specify its behavior. So the first one, obviously, is going to be the Young's modulus, which is what we see in the figure there. Okay, so the Young's modulus, at least visually, you can see is the slope of the stress strain curve. But what it represents, the Young's modulus represents how well this material is able to resist deformation. So higher values of the Young's modulus means that we have essentially a stronger, tougher material that's not able to that's going to resist deformation for larger values of stress. and hence larger values of the external forces. Okay. Okay, so that's pretty straightforward. We did mention that before, but just to kind of give you an example. Right, so when people typically think of a strong metal or a strong material, steel is usually one that comes to mind. Right, so for steel, the Young's modulus for steel is about 200 gigapascal. Okay. So that's pretty high. If we compare that to a fairly softer metal, which is copper, right, so copper only has a Young's modulus of about 130 gigapascal. And so just based on the Young's modulus alone, we can see that steel is a much stronger material. It's going to take a lot more force in order to cause it to form. Okay. So Poisson's ratio, pretty straightforward. It's just a metric of how strong the material is. Okay. But we also need to specify the Poisson's ratio. So traditionally, this has the symbol nu, which is kind of this like fancy V. Okay. Now, Poisson's ratio, this material property is only really relevant when you have multidimensional deformation. So in 1D, in 1D deformation, there's no concept of a Poisson's ratio because it just doesn't make any sense. Okay. And so the Poisson's ratio will basically measure how much a material will deform in directions that are perpendicular to the forcing. So because of conservation of mass, right, we know that whenever we, stretch or compress a material and it gets either longer or shorter, right, it's not like we're destroying mass or creating new mass, right? And so that has to come from somewhere. And so what tends to happen is that when you make deformations or large amounts of deformations in one direction, that usually causes a small amount of deformation in the other one. So we usually call this phenomenon either necking or some ballooning out. Okay. So for example, right, so let's say we have a piece of material like this, and let's say that we stretch it out. We apply a tensile force on both sides of the material. Okay. Right, so generally what we expect, and so, and this is assuming that the tension force is sufficiently large, right? We expect this entire rod to stretch out. And so the new length is going to be something like that. Okay. Okay. But you can see here, and so I did this pretty intentionally. It kind of looks like I was just a little bit sloppy, right? But you can see here that I've intentionally made the rod a little bit thinner as it lengthens out. Okay. And in fact, it's not uncommon to see a phenomenon like this. Okay, so as you stretch this out, right, the entire rod is getting longer, but in order to create that mass, or we're not creating the mass, in order to kind of make that length longer, we have to make the rod skinnier in some places as well. Okay, so this phenomenon here, all right, so essentially we're causing a neck, right? So that neck is essentially a deformation that's perpendicular to our main deformation mode, which is kind of longitudinal in this case. Okay. So how much a material is likely to do this, and the degree in which it does this, is governed by the Poisson's ratio. So what's interesting about the Poisson's ratio is that it literally is a ratio. So it's a dimensionless number, okay? And it actually has a specific range. All right, so Poisson's ratio, typical values for, I would say, a typical engineering metal or engineering material is usually around 0.25 to 0.35. Okay, so most metals are going to fall into that category. So the structural steel that we used for activity one yesterday had a Poisson's ratio of 0.3. Okay, so it's very firmly kind of in that range. The minimum value for the Poisson's ratio is 0. So some materials have a Poisson's ratio of 0, which essentially means that there is no perpendicular deformation. Okay, so it's going to resist that quite a bit. Or in some cases, there's just no kind of perpendicular kind of deformation, even if you do stretch it out. So very soft materials like rubber typically have a pretty low Poisson's ratio. Okay. Right, and the maximum value for Poisson's ratio is actually 0.5. So for materials that are very incompressible, that just have no ways to kind of stretch stretch the bonds between their molecules, will have a high value Poisson's ratio of 0.5. Okay. So if you are using a linearly elastic material that is isotropic, these are the only two properties that you have to define. So it's actually very straightforward, very, very easy. Okay. All right, any questions on the Young's modulus or the Poisson's ratio? Okay, good. All right, so technically there is a third quantity that is there, right? And I think we saw it briefly yesterday, which is the shear modulus. Okay. Question from the chat. So what would be a material with a Poisson's ratio of 0.5? So these are going to be your very hard materials. So something like stone, which is not known to to be able to stretch at all, something like that. Yeah. Mhm. Okay. So there is a third property called the shear modulus, which is, as you can kind of guess, it is a measure of how much your material can resist shear strain and shear deformation. So the shear modulus is given by the symbol G typically. Okay. So technically speaking, you can specify this differently, and there are some materials that have a different shear modulus. But typically speaking, we can compute the shear modulus based on the Young's modulus and Poisson's ratio, and this formula does work for most materials which are isotropic. Right? And so this is the formula that ANSYS uses, and so ANSYS uses the formula G is equal to our Young's modulus E divided by 2 times 1 plus nu. And so what you'll see is that after you apply or after you specify the Young's modulus and Poisson's ratio for your material, the shear modulus is computed automatically using this formula here. Okay, you can overwrite it, so you can overwrite the formula that's in ANSYS if you have a material where you know what the shear modulus is. But if you don't really have a reason to, then you can use this formula to compute the shear modulus. Okay, so when you're in multiple dimensions, 2D, 3D, the shear modulus is used to compute how well your structure will resist shear. But again, it's computed automatically based on Young's modulus and Poisson's ratio. Okay. Okay. All right. So that's the standard three, right? And so that's what you're going to specify for most materials that you're going to use in this class. But what you typically may not know is that this type of material model is what we call isotropic elasticity. Right, so isotropic is a very key word, which basically means that the strength of the material is the same in all directions. And so it doesn't matter which direction that you're going to be forcing your material, you should see the same behavior in all directions. All right, and so if you have a cube of isotropic material, so let me actually draw three cubes here, just kind of illustrate it. Assuming that all three cubes look the same. Okay, they look a bit different. So it doesn't matter, right? If you load the cube this way, if you load the cube this way, if you load the cube this way, okay? So those are the kind of the three primary directions of loading. So we have loading in the Z direction, the Y direction, and the X direction, right? You should observe the exact same amount of strain and stress. Now, granted, the strain and stress are going to be in different directions, but the magnitude of the stress and strain is going to be the same in all of these for an isotropic material. Okay. So isotropic just means that our strength is the same in all directions. Okay. Okay, so what types of materials are typically isotropic? So most of your engineering metals are going to be isotropic, right? Because the way that metals are, the way that their molecular structure is formed, metals have a very uniform and very kind of rigid molecular structure, and so it doesn't matter which direction you're going to push those molecules together in, they're going to exhibit the same properties. Okay. But if your material has some kind of feature within it that expresses some preference for directionality, then it's most likely not going to be an isotropic material. Okay. So for example, so one very common engineering material, especially if you're in especially if you're in building construction, is wood. Okay. Right. So wood, as we all know, comes from trees, right? And trees have distinct fibers that run through them, right? So those fibers are used to transport water and nutrients along the tree, as it kind of grows. All right, and of course, I'm assuming that we have pure wood here. I know that there's particle boards, which are basically just a bunch of sawdust that they kind of compress together. So I'm not talking about that. So I'm talking about kind of pure wood here, right? And so those fibers are going to affect the material properties of that wood. Okay. Most specifically, the fibers are going to add strength within the direction of whatever direction that they are running in. And so this is utilized. And so, for any type of engineering application or construction that utilizes wood, right, you have to be aware of the directions of the fibers. And oftentimes you're going to use that to add strength in a particular direction. Or let's say that, for your application, you're going to apply loading in a particular direction more often, right? That's the direction you want to run the fibers so that you have strength in that direction. Okay. Um, so there's applications for that, but that also means we need a different material model to use wood. We can't just use a standard isotropic material because it's not going to be accurate for describing the behavior of the wood. So there are ways, and these ways are programmed within ANSYS that you can easily access to account for directionality in your material properties. Okay, there's a lot of options actually, but we're going to cover kind of the two, I would say, more simple ones. I say simple, but even just using the first one of these is actually very complicated. Okay. And so this is still assuming linear behavior, right? So linearity of the material is different from its whether it's isotropic or not. Okay. So these two options here are still linear materials in the fact that stress and strain are still linearly related to each other. It's just that the relationship is going to change depending on the direction that you are doing the loading. Okay. So the first option, the simpler one, is called orthotropic elasticity. So this, I think, is typically the one that people think of when they think of, materials that are not isotropic. So orthotropic elasticity allows you to specify different moduli and different Poisson's ratios in each of the Cartesian directions. Okay. In total, if you're going to have an orthotropic material, an orthotropic material requires 9 parameters to be specified. Okay, so basically you're going to be specifying Young's moduli in each of the Cartesian directions, x, y, z. You also need to specify, excuse me, you also need to specify, sorry, I swallowed a spit. You also need to specify Poisson's ratio in each of the 3 directions. And because we can have different values of the Young's modulus and Poisson's ratio in each of the different directions, we no longer have a simple formula that we can use to compute the shear modulus. And so the shear modulus is something that you have to specify manually as well. So you need to specify shear moduli in all 3 directions as well. Okay, so that's a lot, right? And so if you compare that to our traditional linear elastic isotropic material, that only required 2 parameters to be specified, which is just the Young's modulus, which is a global Young's modulus that's going to apply in every direction, and a single Poisson's ratio, which again is going to apply in all directions. Okay. And when we can assume all that symmetry, then we have that formula from above that computes the shear modulus for us. Okay. So even just going from a isotropic material to orthotropic, there's a lot more work that we have to do to specify all these parameters. Okay. But orthotropic elasticity is great. If you are using a wood material. In fact, there's in the past, students have used wood, like balsa wood for their final projects. And I think at the time there was a publication that we use that gave you the orthotropic parameters for certain types of wood. Okay. And so in those situations, you can just look those up and just plug those right into ANSYS and then run your simulation from there. Okay. So orthotropic elasticity is kind of the first step that you take when you are acknowledging the fact that your material is going to have different behavior in different directions. But you can see it's already kind of a big step up. Okay. Okay. Any questions on orthotropic elasticity so far? Okay. All right. So the next step up, which is a big step up, is what's called anisotropic elasticity. Okay. So anisotropic elasticity, the idea behind it is the same, right? And so it's going to allow us to specify different strengths in different directions. But the difference between anisotropic and orthotropic is that we are not going to assume any symmetry between the different stress states. Because even in orthotropic elasticity, and it's not something that's typically stated, but there's actually a lot of symmetry assumptions that's made in orthotropic elasticity to get the parameter list down to none. Okay, so when you don't assume any elasticity, you are actually need to specify every single material parameter that's out there. Okay. And and you may have covered this in solid mechanics, but the matrix of material constants, if you assume no symmetry at all, is actually a four-dimensional tensor, which is very hard to visualize what a four-dimensional tensor actually looks like. But basically, everything in that tensor needs to be specified manually. Okay, so how many parameters is that? It's 27 different parameters. Which is a lot just for one material. Okay. And you have to assume that, if you are going to use an anisotropic material, right, you need to source those parameters from somewhere, right? So you either need a publication or a material data sheet that computes those. It is very hard to find a reliable source that can compute all 27 parameters exactly. Okay. So anisotropic elasticity, it's implemented in ANSYS. Just because there's a mathematical basis for it. It's within the solid mechanics equations. But I will say that it's very rare to actually use this for anything practical. Just because the amount of data that's out there for a purely anisotropic material is not that much. There's very few that's out there. I would say probably the most common application for a purely anisotropic material is kind of more for just academic curiosity. And so for people that are, that they just want to test and see, what if we were able to modify this parameter this way for this material, then how would that affect our results? Okay. But for most, everyday use of finite elements with materials you can find, in a typical engineering setting. Very few materials is anisotropic. Okay. The only one that I can really think of off the top of my head are just any kind of weird kind of biological or maybe viscoelastic material. You may want to use anisotropic for that. But for the most part, it's very rare that you would use something. Okay. Okay. Another aspect to consider, and this is a factor for consideration for both orthotropic and anisotropic elasticity, is the limitations and how ANSYS will allow you to specify this. Okay, so this isn't in the notes, and so this is just a difficulty that I've kind of noticed just kind of observationally over the years. Okay. So when you apply these material properties, any kind of directionality in your material properties within ANSYS, right? You're limited to the directions of the Cartesian directions. Okay. And so in the most naive way, so let's say that you're applying an orthotropic elastic material, right? You're applying a Young's modulus in the x direction, in the y direction, in the z direction. Okay. Now that makes sense mathematically, right? So for forming the equations, that's typically how we form them. But there are some practical difficulties that show up if you're applying this directly to a CAD. Okay. So what I mean by that is that, if you're applying these parameters in those directions, you have to align your CAD model in that direction as well, so that the strength that is in, let's say that you're doing a wood material that's going to have increased strength in the X direction, you need to align your CAD model so that the fibers actually run in that X direction as well. So for example, right? So let's say you have a material, it's made of wood, right? It has fibers that are kind of running in this direction here. Okay. If you wanted to run a simulation on this in ANSYS, right, you have to align your CAD model and you have to kind of arrange for that to align perfectly with how you define the material properties so that the increased strength is in that direction. Okay. So when you're importing your CAD model, you want to make sure that the X direction of what you import in is in this direction here. Okay. And then when you plug in the material properties or when you put those into the software, it's also in that direction. Okay. But then, you may ask the question of, what if you have a complicated structure where you have the fibers running in different directions for different components of your structure, right? Well, there are ways around that. You can assign your material properties according to the local coordinate system of a specific component, okay? I had one student do this quite a few years ago, 4 or 5 years ago. So there are ways around it. So let's say that, if you have a structure that has, multiple different fiber directions, you want to make sure that they're, specified appropriately. So there are ways around it, but it does get quite a bit complicated. I do have a handout that's actually on Canvas already that shows you how to apply an orthotropic material, but it is for a very simple case. It's literally just for a cube. And so, if you do have any kind of complexity, just be aware that there are additional steps that you have to run in order to make sure that your strength is appropriate in each direction for each component. Okay. Okay. Good. All right. So that's everything that has to do with directionality. Okay. Next thing I want to cover with respect to material properties is plastic deformation. Okay. So let's kind of rewind a bit and let's go back to assuming that our material is isotropic and linear. Okay. So for most jobs that we're going to run in this class, an isotropic linear material is perfectly adequate to get the results that you need. Okay. And so for such a material, right, we already know what its stress strain curve is going to look like. So we know the stress strain curve is going to be linear, right? Where the slope of that line is the Young's modulus. Okay. So for a purely linear material, we're basically just kind of moving up and down this curve here, right? So the amount of strain that's experienced is directly proportional to the stress. Okay. Okay. But this linear relationship, as you probably know, as you can probably remember from your solid mechanics class, is only valid if the magnitude of the strains are relatively small. So another way to say that is that this linear portion of the stress strain curve only really exists, close to the origin. Okay. And so if you were to strain your material past a certain point, then we kind of break this linear relationship and then we kind of enter what's called the plastic region. Okay. Okay, so for every material, there's a certain point where this linearity kind of starts to break down. Okay. So this point we often call the elastic limit. So the elastic limit is the maximum stress that the material can sustain while it's still having this linear relationship. Okay. You can also say that it's the maximum strain as well. Past that elastic limit, our stress strain curve starts to change shape. Okay. Instead of being a nice linear line, the curve here kind of starts to taper off. So it kind of almost starts to look like the curve of the square root of x. For this region right here, right? So if we look past this region where that linearity starts to get broken, is what we call the plastic region of deformation. Okay. So a lot of things change within the material once you get past that elastic limit. Okay. First of all, the first thing that changes is obviously the stress strain relationship is going to be different, right? So we don't have this linear, relationship between the two. Okay. Another thing that changes is that if you push past the elastic limit and if you were to release the load, right? Releasing the load anywhere within the plastic region is not going to return the structure to its original state. Okay. Okay. So you've probably seen this a million times at this point, but let's say that we stress the structure such that we get our stress strain into that plastic region. So I've indicated that with the orange dot. Okay. If you were to release the load at this point, right, we're not going to go back to the origin. Instead, we're going to go to a point where there's going to be some residual strain. Which, by the way, the slope of that line is also the Young's modulus. Okay, we're just starting from a different point. And so if the loading is released in the plastic region, we return to a state with some residual strain. Whereas that's not necessarily true in the linear region. So in the linear region, so let's say that the magnitude of our stresses and strains is relatively small. If we were to release the load, we actually return back to our original configuration. Okay. So that amount of deformation, that amount of residual strain is what we refer to as plastic deformation, and we can't exactly recover from that. Okay. Now, so how does this relate to ANSYS, right? So in its default state, which is the state that we use ANSYS in activity 1, and which is going to be true for activities 2 and 3 as well. In those situations, plastic deformation actually is not taken into account. So this statement here has a number of consequences. Okay. First of all, right, you have to kind of remember that all the time. And so whenever you are looking at an ANSYS result, you have to ask yourself, or you have to kind of actually look at the magnitudes of deformation and check to see if the magnitudes of deformation are reasonably small. So this is something that you have to check. You have to explicitly look at. Okay. Because sometimes ANSYS will give you a warning. Sometimes ANSYS will say that the deformations that it's experiencing is very large, and so it may tell you to look at it again. But sometimes it may not, right? And so, for example, so let's say that we have a beam like this, okay? Right? We're applying a force here, okay? And so if you were to look at just the pure ANSYS results, right, you may see something like this, right? So you may see like a blue region here, maybe like a green region here, maybe like a yellow region, and then orange, and then red. Right, so that would be the deformation point, which is what we expect, right? And so without putting any numbers on this, right, if we have a beam that we know is fixed on the left-hand side and we're applying a force on the right, right, we expect the deformation to be highest around where we're applying the force, right? So there's nothing, at least from the color deformation here is nothing, there's nothing alarming, right? That's exactly kind of what we expect, which is kind of very similar to our plate with the hole, okay? What you really need to look at, right? You actually need to look at the color bar and see what the maximum deformation actually is, right? Right? And you have to ask yourself, you have to kind of use your own kind of engineering intuition and ask yourself if that value is actually reasonable, okay? So one way you can check, right? You can check that value against some kind of physical dimension of your geometry, that you're looking at, okay? So, for a cantilever beam like this, one physical dimension is the overall length, right? And so if the maximum deformation is on the same order or similar to that maximum length, or even worse, if that deformation is greater than that length, then you might want to think about, maybe your results are not that reliable, right? Because what ANSYS does, right? Unless you actually specifically tell it to account for plastic deformation, it's just going to follow that linear trend all the way up until infinity. Okay. Okay. And so you'll see this in activity too, right? So what linear basically means is that, as you increase the loading, right, the amount of deformation is going to increase proportional to that. Okay. So if you double the amount of load, right? So if you double the amount of force that you're applying onto a structure, then your deformation is also going to double as well, right? That's what the linear relationship means. Okay. Same thing if you triple it, if you have it, right, you multiply by 10%. Okay. Unless you tell ANSYS otherwise, ANSYS is going to assume a linear, you know, linear behavior. Okay, which is kind of dangerous on the one hand, right? Because you know it's not going to warn you, or it's not going to tell you whether or not your assumption is going to be valid or not. Okay. But on the other hand, it's kind of understandable because a linear material is actually the fastest to compute. As soon as you add some complexity in here with regards to plastic deformation, with regards to nonlinearity, your simulation actually starts to become more expensive. And so the way that ANSYS is typically designed, ANSYS is designed to give the users kind of the path of least resistance, right? And so it's designed to kind of take you from a geometry, apply the simplest settings that it can in order to get you a result. Okay. So you saw this a little bit yesterday as well. So, when we tried to do the default mesh in ANSYS without applying any settings, so without applying any settings for the sizing or the method, right? We were able to get a mesh, but the mesh that we got, I would never say is appropriate to run a practical reliable simulation. Okay. So the choice of material model is the same, right? So ANSYS is always going to pick the simplest way to give you a result, but you kind of have to be the judge to see whether the result that you're getting is actually reliable and accurate. Okay. So if you want specific thresholds, of course, it's going to depend on, your specific application. But the threshold that I typically use to at least give a behind the napkin kind of estimation of whether these results are reasonable, I check to see whether the maximum deformation is within 10% of, let's say, the maximum length of your entire structure. Okay. Not within, we say less than. Usually. Oh, go ahead, Carlos.
Is that why ANSYS doesn't have like a factor of safety to solve for, like SolidWorks?
You can solve for factor of safety in ANSYS. In fact, we'll do that on Tuesday. So on Tuesday on activity two, I'll show you how to compute factor of safety. But you have to keep in mind that factor of safety is assuming this this linear property here. Yeah. So the
Okay,
way
thank you.
factor of safety is that it takes the stress that it's computing and it compares that to the yield strength of the material, which you can do manually. But ANSYS kind of does it a bit more conveniently as well. So you can do that. It's just you just kind of have to keep this in mind. Okay. So I can't stress this enough because I think what happens a lot is that people use ANSYS and they get very, very large deformations, and then you have to kind of tailor back and say, like, maybe this isn't reasonable based on our assumptions here. Okay. All right. Any other questions on this here? Okay. And by the way, and I want to emphasize that 10% rule is just one that I personally use. That one's not it's definitely not an industry standard at all. And so different industries or different applications will have different thresholds for this. But it's at least a good kind of sanity check for you to check. Okay. Okay. So another thing that you can do, right? So certain materials will actually quantify where that elastic limit actually is. And so another thing you can do, right? Which is a little bit more precise than just kind of the 10% rule that I just mentioned, is that you can check the von Mises stress within your structure after you run the simulation and check to see whether you run past that elastic limit. So for certain materials, and so if you're using a fairly common material like aluminum or steel, the elastic limit for those materials are fairly well known. You could probably look it up in the material data sheet. And so kind of a more precise way to see, whether you're good, is just to check that elastic limit. And so as long as the stress is below that elastic limit, then you're good. The linear assumption is just fine. Okay. Now, what do you do if you do run past that elastic limit, or what if you have very large deformations? Okay. ANSYS does have the capabilities to simulate this. You just have to enable. Okay. Okay. So there's a couple of things that you can do. Some more easy than the others. Okay. So, remember one thing that's characteristic of the stress strain relationship, once you push past that elastic limit, is that your stress strain then becomes a nonlinear relationship. Okay. So ANSYS has a very easy way to turn this on. So if you go to the settings within the simulation itself, which I say that as someone that's done this, but I know you guys have never seen it. But there's a section within ANSYS Mechanical where you can change kind of global settings. There's a way to enable large/nonlinear deformations. Okay. So I'll show you that setting on Tuesday. It's actually very easy to activate, but just be aware that it does make your simulation a little bit more expensive. Okay. Again, probably not noticeable for the jobs that we're running now, but it does add a bit of cost. Okay. But you also have to keep in mind that you can only use this feature if your material model does have the nonlinearity already programmed in. Okay. Right, so not every material is going to have this, especially especially for a material that you're going to specify manually yourself, which I'll show you how to do that on Tuesday. Usually this is something that relies on a lot of kind of empirical data. Okay. So usually if you're going to be specifying your material yourself, it's not going to have this behavior enabled. But if you're using a material that's already programmed within ANSYS itself, like structural steel, it should have that behavior. Okay. Okay. And number two, so to fully specify the nonlinear behavior of material actually is a bit cumbersome. There's a lot that's involved in it. But the smallest thing you could at least do is you can at least program in the change in stress strain behavior within the plastic region. Specifying the plastic behavior. All right, and so this is of course assuming that your material doesn't have this already implemented. So this is maybe for a material that you're implementing yourself. Okay. All right, so you have two options here. So the simplest way to implement plastic behavior is to use what's called a bilinear stress strain curve. Okay. So under the bilinear stress strain curve, we are basically conceding, or we're assuming that the stress strain relationship is changing in the plastic region, but it's also still going to be a linear line. It's just going to be a linear line with this with the different, usually lesser slope. So this, of course, is the simpler way to implement it. And if you've seen any kind of stress strain curve for plastic deformation, it's not a line. But for just a very simple, kind of straightforward way, without the implementation of a lot of different data points, this will work in a pinch. Okay? And so basically, the stress strain curve in this situation looks like this. Okay? So we have our first linear region. So that is our elastic region, where we have stress strain that's related by the Young's modulus. Okay. So under the bilinear, or using the bilinear setting here, once you're past the elastic limit, then all we do basically is we just add another line there, but with a different slope. Okay, so the plastic deformation is just governed by another linear. Okay. Okay, so again, that's the simplest thing you can do. Sometimes that's the only thing you can do. So if you're using a material that's a little bit exotic, right, you may not have all the data points to specify every region within the plastic deformation zone. And so maybe all you can really do is just add a second slope. That's kind of the average effect of the plastic deformation. Okay. Okay. So that's one option that you can do. The other option is you can use what's called the multilinear approach. Okay. So in a multilinear approach, instead of just a single linear line to describe the plastic region, we are now describing multiple linear lines where we can change the slope in each one. Okay. The downside to the multilinear approach is that you do need to add lots of data points, right? And so usually this is an option where let's say that you're performing material testing at your engineering company, and you have these data points that from your, let's say structural biaxial testing. Okay? And so the multilinear approach looks something like this. And so we have our initial linear zone here. Here's our elastic limit. And so from here, maybe we have multiple lines where each data point there is maybe a test that we've run. Okay. So usually for the most part, if you're implementing your material properties manually, I would say the most common case for this is, let's say you work for an engineering company that uses some kind of proprietary material that the company develops, like let's say some kind of composite material. And so those will be situations where you need to input your own material properties here. And so what we covered today, just, I will say it just kind of scratches the surface in terms of what ANSYS can do. There is a lot of options for material models within ANSYS. So, for the most part today, I mostly just want to make you aware that there are options for all these things. Unfortunately, we don't have time in this class to go over everything. And to be quite honest with you, I don't have the expertise to cover everything with enough respect and detail. I'm definitely much more of a fluids guy than a materials guy. But those options are there. And so, if you either for your as soon as your final project, or maybe, you use ANSYS for your professional work, just know that these options are there if you need them if you're using an interesting material. All right, any questions on this? Okay, all right. So the last thing I want to mention before we head out is this concept of hyperelasticity. Okay, so hyperelasticity. I think I've asked this question in the past, and I think nowadays you guys are learning a bit about hyperelasticity in your classes. But I remember when I was in college and I took my strength and materials, hyperelasticity was not covered at that time. Not that it wasn't a thing; it's been a thing for a long time. It's just a little bit more advanced than your linear, stress strain curves. Okay. But hyperelasticity is a completely different kind of material framework, a completely different way to relate the stress and strain within a material. Okay. So I'd say that, traditionally, just because it's more simple, for the most part, when you first learn about these concepts of stress and strain, linear elasticity is what's taught just because it's the simplest to understand. But linear elasticity does have its limitations. And so I would say, for more traditional engineering materials like metals, linear elasticity is a great framework. But I think what we're seeing nowadays is that there's a lot more interest in, let's say, composite materials, and more kind of biological materials that don't necessarily follow a linear stress-strain relationship, even for very modest deformations. Okay. So for these situations, a different type of way to model the material was needed, and hyperelasticity is one way to do it. Okay. Now, I can't say that I'm an expert in this at all. I really only know about it just from a surface level perspective. But, again, this is something I just mostly want to make you aware of. Okay. But the way hyperelasticity works is that instead of having an explicit formula that relates the stress and strain, instead, what we have is the concept of what's called a strain energy function. Okay? And that strain energy function, you can think of it as almost like a potential energy, right? So the strain energy function tells you how much potential energy is within the material. And as you stress it and as you deform it, then that potential energy gets kind of used up in different stress states. Okay. And so the strain energy function, you can take derivatives of that function in order to get specific stress and strain. Okay. So again, the idea, and this is just me just kind of looking at it from an outsider's perspective. I haven't really done much with hyperelasticity in my work. Okay, but the idea is that every material has a certain amount of potential energy that gets conserved as the object or as the structure undergoes different states of deformation. Okay? So essentially, as a material or as a structure is subjected to external forces and constraints, right, it's going to deform. right? And then as it deforms, then the potential energy or the strain energy function is conserved, okay? And so the way that a structure is able to choose its deformation state or the geometry or the configuration and the stress distribution within the structure, it's chosen in a way to minimize the strain energy function. So I know that's not the best description, and this is not going to be the best analogy. But one analogy that you can think of is the potential energy that's associated with gravity, right? And so gravity, potential energy, we all know, we learn all that in basic mechanics, is just the mass of the object times gravity times the height, right? So every object has a gravity potential energy if it's held at a specific height, right? So I can take this roll of tape right here and hold it up, right? And the potential energy that it has is governed by how high it is leveled. Okay. If I were to release this roll of tape, right, it's going to choose a position that minimizes its gravity potential energy, right? And so that's a very fancy way of saying that the roll of tape is just going to fall, right? Because the state of which this roll of tape has the minimum gravity potential energy is on the ground, where it has no height. Okay. So that's a very simplistic way of saying that, when, a structure, right, that's governed by hyperelasticity that has the strain energy function, when it's being subjected to external forces, it's going to choose a state of stress, it's going to choose a state of deformation that minimizes the strain energy function. If that kind of helps you visualize kind of what this is kind of going on. Okay. So kind of the upshot for this is that, with hyperelasticity, we kind of break out of this kind of these shackles of linear elasticity, where we can have nonlinear stress strain relationships right from the get-go. Okay. Another thing to note is that in hyperelasticity, there's no concept of plastic deformation. And so it's literally just a completely different framework for modeling stress strain within a material. Okay. And so if you were to draw it out, right, you may have a stress strain relationship that looks maybe something like this. Okay. So I've used I've used hyperelasticity once for kind of a relatively small project. I use it to model the stress strain relationship in biological tissue. So essentially, I was modeling the deformation of blood vessels in response to blood pressure. And so biological materials, not traditional engineering materials at all. And so the idea was to use a hyperelastic material that can better capture its stress strain relationship. Okay. I didn't get too far. And so that's kind of the extent of my knowledge of hyperelasticity. But it is, if you are using kind of a non-traditional material, hyperelasticity is definitely something to look into. Okay. All right. Any final questions before we wrap it up for the week? Okay. All right. So that's all the time we have for today. So thank you guys for coming today. We're going to come back on Tuesday. So Tuesday is going to be our next ANSYS activity. And so if you want to participate in the class, please make sure you're here. But of course, participating on Zoom is fine as well. Just be aware it's a little bit harder for me to get around to you for that. And then from there, we'll continue on talking about more finite elements. So hope you guys have a good weekend. It was great meeting you all this week. And yeah, I'll see you guys next week.
Thank you, Professor. I did have one question. It was in regards to the assignment, if you got a second.
Sure.
Okay, just really quickly, when I went to go do the last analysis where we go back to the 50 millimeter hole, and then change the size of the mesh. I just wanted to make sure that I was correct in deleting the refinement and the edge and the plate sizing, because we had set those individually so that it was 3 and 5 and then had the refinement. And those were
Yeah,
stopping it from actually updating the mesh when I went to adjust it. So I just want to make sure that was right.
yeah.
Okay,
That's fine.
so it would just be the mesh with its fixture and its load applied to
Exactly.
it. All right, perfect. I did it right. All right, thank you, sir.
Yeah,
Okay, I'll see you next week.
yeah. See you next week.
Okay.
Maybe we should have a good one again.